to Nkung Public Lecture organized by the Institute for Mathematical Sciences, IMS, and the National University of Singapore. My name is Su Chen-po, and I'm the Deputy Director of IMS. I will start by briefly introducing our Institute IMS and its main activities. IMS, which was founded in the year 2000, is a university-level research institute dedicated to the fostering of mathematical research. Its mission is to link mathematical sciences with other disciplines, nurture the growth of mathematical expertise, and provide a platform for research interaction between the mathematical community in Singapore and a wider international community. In carrying out its mission, IMS organized thematic research programs chosen from areas at the forefront of current research in mathematical sciences and their applications. IMS also organizes conferences, standalone workshops focusing on specific topics of current interest, as well as distinguished lectures and a summer school. As part of its outreach program, IMS organized public lectures like the one today, as well as school lectures. Through these means, IMS seeks to raise public awareness of the role of mathematics in science, engineering, technology, and industry and commerce, and to encourage talented students in the study of mathematics, leading to research careers in the mathematical sciences and their wide applications. So now I will yield to the chair of today's public lecture, Professor Alan Ray, who will introduce our distinguished speaker.
Well, it's a great pleasure to be here today as part of a workshop that's been happening at IMS with my fellow co-organisers, Regina, Eamon O'Brien, and Sarah Cannon. It's a great pleasure to introduce John Millenberg here today. He is the John D. MacArthur Professor and the Vilas Distinguished Achievement Professor at the University of Wisconsin-Madison. And moreover, from 2019 to 2025, he is the A.D. White Professor at Large at Cornell University. He got his PhD in 1998 at Harvard under the direction of Barry Meza. He then went to Princeton and held several positions before moving to Wisconsin in 2005. He's been awarded Sloan Fellowships, Guggenheim Fellowship, and is a Fellow of the American Math Society. Jordan's main research interest is in arithmetic geometry, but Jordan's really a true scholar. He's mathematically very curious, and he's got interests in papers in combinatorics, representation theory, harmonic analysis, algebraic topology, and my own favorite, the topology of tree manifolds, and that's just to name a few. Recently, he's also been interested in applications of machine learning in mathematics. Now, if that's not enough for you, Jordan is actually a best-selling author. His book, Shape, was a bestseller in the New York Times, and part of the review says the following: a clearly enjoyable and insightful book. He has 2 other books and has got great experience in writing mathematical articles, popularizing mathematics in many newspapers. He has a reputation, which I'm sure we're about to see, as a gifted expositor for popularizing mathematics. And today he's going to talk about From Mosquitoes to ChatGPT, the birth and strange life of the random walk. Jordan.
Wow, well, thank you guys so much. It's great to see so many people, and what I'm told is a vacation month here in Singapore. This is my first time here. I'm having an amazing time. I just was at the Hopar Villa this afternoon, so I'm in kind of a cosmic mood. If you guys know it, you can go there and sort of see the entire cycle of birth, death, and existence. And I guess we'll just try to keep that energy going through today's talk. So let me start, because I think it's always good to start a math talk with a puzzle. So the puzzle is a simple one. It's, what is this list? Kendi, Jean, Abby, Florimera, Jean, Starlo, Kaming, and Betelia. All right, well, you don't really have enough information to answer this question, but I'm going to sort of put this, and then we'll sort of circle back to sort of talk about what this strange list is at the end. But the other thing you do that I like to do in a talk like this, is tell a story. I mean, as Alan said, I write these books that are about math for the general public, and when you write a book about this stuff, just as when you teach in the classroom, in the end, you're telling some kind of story, a story about mathematics. And so let me start this story right here. And I think this is probably not a famous face, but this is Sir Ronald Ross. He was the second winner ever of the Nobel Prize for Medicine, and maybe you can guess from this kind of a somewhat blurry little chunk of text that I have here, which says, if you can read the headline, it says, "Mosquito Man Coming." Why did he win the Nobel Prize for Medicine? He won it because he was the person who discovered that malaria was transmitted by mosquitoes. He discovered the transmission mechanism of malaria. And interesting, we could talk a whole hour about this guy because he's a very interesting character. So he was this extremely esteemed man of medicine. He was this newspaper clipping you see, which says "Mosquito Man Coming," is from the St. Louis Post-Dispatch in 1904, and what it's referring to is that Ronald Ross was being invited to St. Louis to speak in the Louisiana Purchase Exposition. It was this sort of huge fair that took place in St. Louis in the United States, which was sort of meant to sort of put the United States on some kind of bigger footing in the world than it had been up till then. So they sort of invited all these in sort of an incredible list of like scientific and literary dignitaries. Among them, Henri Poincaré, actually, who's a big character in my book. He won't be such a big character in this talk, but for the people coming to the Thin Groups conference, I thought I'd throw his name out there. All coming to St. Louis to talk about the scientific, artistic, and literary achievements of the day. And Ronald Ross, for all that he was sort of so esteemed and so honored as a doctor, you guys probably know people like this. He was kind of bitter. He never felt like it was enough. He never felt like he was getting enough credit. And part of that was that he didn't actually seem to really value medicine that much, even though obviously he had great achievements in it. There were two other things that he valued more. One, he really wanted to be a poet. He wrote a lot of poetry, but probably even deeper than that, he really wanted to be a mathematician. That was what he really valued. And he always felt that somehow being a doctor was like not as good as this. So what he says in his memoirs about coming to give this talk is that he was invited to come give a talk about medicine to this group of medical men, and instead he gave a talk about mathematics of which no one in his audience understood a single word. And he said that with pride. I mean, this is what he was trying to do. So I will try not to bring that attitude to you guys tonight, but this was certainly Ross's attitude. So let me show you a diagram so this is a diagram from his talk. So let me give a little background to explain what we're looking at here. So once you understand that malaria is being spread by mosquitoes, then obviously a thing that you want to do is eradicate the mosquitoes, right? If you're sort of trying to institute some kind of malaria control in some kind of region. But of course the problem is that when you eradicate mosquitoes, they come back. And so what you might want to know is if you can eradicate all the mosquitoes from a certain area, how long do you have? Like how long do you have before the mosquitoes repopulate the area? And so this is a picture of a sort of mathematical model that Ross made for this problem, which is that what you're seeing is this, when you look at these sort of concentric circles here, the center of the middle circle is supposed to be the fetid bog where the mosquitoes are spawning. And the question is, if mosquitoes are being born there every day, how long does it take before they fill up this entire region? And so another way to ask that is like, how far is a mosquito going to go from where it's born in a certain amount of time? Well, if we make a mathematical model, we have to simplify a lot of things, right? So one question we have is like, how far can a mosquito fly in a day? So you might say, well, if the mosquito flies a mile in a day, maybe in 3 days it flies 3 miles, or maybe in 5 days it flies 5 miles. But that model is not good enough. Because your mosquito, as you may know, is like not really like a goal-oriented individual. Right? The mosquito is not going to sort of pick a direction and consistently fly that direction, trying to get as far as possible from its birthing point so that it can, fill the whole region with itself. No, I mean, a mosquito, we can model it by saying maybe each day it just kind of wakes up and decides which direction to fly, essentially at random. And that's sort of what is being depicted here. So I have a little light, right? Let me use it. So this line that goes out to the L, that's the goal-directed mosquito that doesn't really exist. This is Ross's depiction of, like, what if the mosquito just sort of flew straight the direction each day? And what Ross says is that actually the mosquito is going to do something like this. It's going to fly out this direction, then maybe it chooses to go this way, then maybe it chooses to go this way, then this way, then this way. And as you can see, where it ends up is actually not, in this particular picture, is not very far from its starting point. So I think we can agree that the mosquito that is choosing its direction at random, sort of meandering around the landscape, is probably not going to stray as far from its original starting point as the mosquito that goes straight. And that's good, right? If you're trying to sort of keep malaria out of the land. But how much more slowly does the mosquito move from its starting point? This is the question that Ross was working on. This was the question that Ross posed to his fairly mystified medical audience in St. Louis, and it was not actually a problem that Ross was able to solve, but he was presenting it at this conference. So this is what he did. He wrote to Carl Pearson. This is maybe a slightly more familiar name. This is the man you see here, sort of one of the great founders of British statistics. He wrote Pearson with this problem of the mosquito and asked, do you know how to solve this? Do you know how to analyze, like, how far the mosquito will go in a certain amount of time? Well, Pearson didn't know, but Pearson said, I'll tell you what I'm going to do. Remember, there's no Google at this time, right? You can't just sort of look up what's known. He's like, I'm going to write a letter to nature. This is what you did. It was kind of like putting up a thing on a bulletin board. He's like, I'm going to write about this problem and I'm going to pose it in nature, but here's what I'm going to do. He said, I'm going to take out any mention of biology, because if I say it's about mosquitoes, like, the mathematicians won't work on it. Everybody's like a little snobby in sort of early 20th century Britain. So Ross said, that sounds great. Like, put it in nature and see if anyone can solve it. And so what you see here is the very letter that Carl Pearson posted, and you will notice that he took out all mention of biology. He also took out all mention of Ronald Ross, which Ross was extremely unhappy about. He sort of presented it as just something he was thinking about. So instead of it being about a mosquito, he sort of rephrases the problem as just being about a person walking. And so in so doing, he introduces this term, the random walk, the very name by which this problem is known today. So, I mean, math is kind of like this. You wouldn't think that this kind of, biological, epidemiological problem and this sort of somewhat peevish decision by this great doctor to sort of go and give a mystifying talk to an audience that was not ready for it, would be the beginning of an entire field of mathematics. But somehow, so it is. The study of random walks, which we're going to talk a lot about today. Pearson poses this problem in the letters column of Nature, and it does not take long before it's solved. In fact, in some sense, it takes about -20 years, because immediately Raleigh, the physicist, sort of writes and said, like, I already know how to do this. Like, I did this in connection with a problem in acoustics. Oh, by the way, I meant to say I wanted to add one piece of local color, which is that this question of sort of mosquito spread is not a finished one. And in fact, here in Singapore, there's a project going on now. It's done differently today, right? So this is not about mosquito eradication. This project, which is has the involvement of Verily, which is a piece of alphabet, which we'll talk about in a little bit, is actually about why Singapore is breeding millions of mosquitoes, because they're breeding male mosquitoes that are made infertile by a genetic modification And so you actually want to sort of fill the world with these mosquitoes that can't breed. But the question is fundamentally the same, right? If you introduce them, how long does it take for them to sort of spread out and fill up the whole population with themselves? So here's the story I want to tell, guys. I just told you what was happening in 1904. That Ronald Ross is working on this problem about mosquitoes. He asked this question to Carl Pearson. Carl Pearson develops the term random walk, and this problem is solved. But another funny thing about mathematics is that sometimes there's a problem that's just somehow ready to be thought about. So at essentially the same time as this is happening, all over the place, people are developing the same set of ideas for completely different reasons and completely independently with no knowledge of the other. So here's another picture of a random walk in the middle, and it's sort of flanked by two scientists. I think one is more familiar than the other, right? Who have I got here? Yes. Oh, somebody know the other one. That's very rare. Wait, who said it? Who said Brown? Nice. Okay. So on the right, we have Albert Einstein, and I always like to use the young, hot Einstein when I give this talk, because I'm not talking about sort of his later life, like as a grand old man in Princeton. I'm talking about Einstein in 1905 when he's sort of starting his career and like looks like this. On the left, you have Brown. The oldest person we'll see today. So Brown is not working in 1904 or 1905. He's working much earlier. But he's the person, he's a botanist, that he notices that if you have like a little piece of pollen suspended in a drop of water and look at it in a microscope, it moves. It kind of like jitters around. This presented a very interesting question. What's making it do that? That sort of natural belief was that, well, somehow, even though it's been taken out of the plant, it has some kind of principle of vitality, like something about it is still alive, and that's causing it to sort of like move around under the microscope. But, Brown, like being a real scientist, was like, well, let me sort of test whether that's true. Let me sort of put other stuff in my drop of water, and see what it does. And he quickly observed that it didn't matter whether the thing he put in the water was originally alive or not. He had all kinds of substances. He put in some ash. He put in some other living things. He put in a piece of bone. My favorite part, he writes this long list of things he put in the water to look at. And I think my favorite part is that he puts in a fragment of the Sphinx. Like, that was just a normal thing to have in your laboratory for somebody with no explanation. He just, like, that was one of the things he put in. And it, just like everything else, it sort of, like, moved around in the water. So this phenomenon, which is called Brownian motion, after Brown, who discovered it, was really for a very long time an extremely controversial question. Why was it happening? But certainly one theory that sort of had a lot of legs was that inside the water there were tiny particles too small for our microscopes to see, that were moving around and whacking into the much bigger chunk of pollen and moving it in this sort of strange, jittery pattern. So this was certainly something a lot of people believed, but there was not really any evidence for it. I mean, how could you it's sort of hard to gather direct evidence for saying there's some particles which we can't see which are doing something. So what does Einstein do at this point? Einstein says, well, at least we can figure out how the particle would move if that were the correct model, if that were actually what was going on. So let's think about that. What would it mean if the Brownian motion were coming from the fact that the piece of pollen or piece of Sphinx or whatever it is being buffeted by these very fast-moving particles in very high number? Well, I guess like at every time interval, pretty frequently, the particle would get whacked by a molecule, as we now call them, coming from a certain direction, but probably a pretty random direction, right? Because they're like all over the place, moving in every which way. So it would get whacked by a molecule and move a certain distance in a certain direction, and then a moment later it would sort of move in another direction, essentially at random. In other words, it would be doing the same thing as Ross hypothesized that the mosquito was going to do. And Einstein was faced with the same question that Ross faced, which is like, if that's what's actually going on, what would we be able to say about the motion? Like, for instance, like how much distance would that particle tend to traverse from its starting point in a given time? And so one of the things that Einstein is doing in 1905 is exactly to sort of show that the behavior of the piece of pollen in the microscope was exactly in conformity by essentially solving the same problem. Well, I was going to say that Ross solved, but Ross didn't solve, but the same problem that Ross and Pearson promoted and that Raleigh had solved, and showed that it fit experiment, giving what was seen at the time as a kind of decisive evidence in favor of the molecular theory of what's going on inside the water droplet. But that's not all. Okay, you guys did great. You got both Brown and Einstein. Do we know who this guy is on the left? See, when I invite French people, of course, they get Bachelier. Oh, and finance, I have French people and finance people in the audience. So we recognize Bachelier, who is not an 11-year-old, although he looks like he is in this picture. This was just how he looked. So Bachelier is another interesting case. So he's a math student in France, but what he wants to work on is considered completely disreputable. He had actually, he didn't have the sort of typical background that people studying math in France had. He was an orphan, and he had sort of worked in industry before he sort of came to study mathematics. He'd worked in the Bourse, like the main bond market in Paris. And he was interested in the motion of bond prices. And, well, you're going to hear me say the same story again. He said, as far as I can tell, these bond prices are essentially randomly moving up and down. And the question is, like, well, I mean, you can say that, but if you want to test that, or at least sort of show that the world is consistent with that, you would want to know what would the long-term motion of these prices look like if they were just choosing whether to go up or down at random. And this was exactly what he worked on in his thesis under Poincaré. It took quite a long time for sort of anyone to really take notice of what he was doing. He lived long enough, happily, to sort of see what he did become, I would go so far as to say, conventional wisdom in mathematical finance, as evidenced by this sort of very big best-selling book by Burton Malkiel that I put up, which sort of, again, brings this terminology of the random walk into personal finance. So again, this is happening, what did I already say? We have Einstein's working in Switzerland in like 1905. Bachelier is working in Paris around the same time. Bachelier doesn't know what's happening with Ross. Ross doesn't know what's happening with Einstein. But we're not even done yet. It's happening in Switzerland, it's happening in France, and it's happening one more place too. You guys are amazing. Who's this? Not Chebyshev. Yeah, this is Markov. Okay. So this is Markov. And the other thing we call a random walk, besides calling it a random walk, is we call it a Markov process after this guy. And this is the person who really does the most to develop the mathematical theory of the random walk as we know it today. And if you thought the other reasons for developing this theory were kind of variegated and maybe a little strange, Markov's reason was the strangest of all. He was trying to win a theological argument. Let me explain what I mean. So Markov, another interesting character, he was sometimes called Andre the Furious because he wrote so many angry letters of a political nature to the newspapers in Russia. He was an extremely vocal atheist, very angry at the Russian Orthodox Church. He became really mad when Tolstoy was excommunicated, and he demanded that he also be excommunicated, which he was. He was kind of the leader of the St. Petersburg School of Mathematics. And his enemy, Nekrasov, was the sort of leader of the Moscow school, and Nekrasov was as devout as Markov was an atheist. So here's what happens. Nekrasov believes that he has developed a mathematical proof that the Russian Orthodox doctrine about free will is correct. He writes a 300-page paper about it. I'm not going to try to summarize it very much here because it's not correct, as you might imagine. But fundamentally, let me give you the sort of one sentence TLDR on Nekrasov's 300-page paper. He says, well, we look around the world and we see that sort of lots of things that happen sort of settle down to predictable statistical averages, right? This was sort of the dawn of the age of statistics. The percentage of male to female births and the age of first marriage and like all these kind of things that measure people's behavior in the aggregate. We see them settle down to averages. Now he also knew the great theorem of Bernoulli and probability, which says that, well, if you have a bunch of independent events, then what proportion of them yield a certain outcome should also settle down to an average. So his reasoning was, well, that somehow means that everything in life is independent, and so free will exists. Don't worry, you don't need to understand it any better than that. But the point is that this made Markov extremely angry. He sort of was at peace with the fact that a lot of people around him were extremely devout. But for it to be dressed up in the language of mathematics, this he could not tolerate. This was not acceptable to him. So he's like, I have to show that this is not true, that things can settle down in a predictable statistical way, even if they're not independent from each other at all. And so that's what he did. I'm going to sort of go back to the mosquitoes and give you a sort of a very limited picture of what Markov did. He said, imagine that the mosquito, instead of having this kind of whole circular range of places it can go, actually only has two places it can live. There's two fetid bogs, bog 0 and bog 1. And his model for the mosquito looks something like this, that, like many of us, it's sort of comfortable and doesn't like to move around too much. So if it wakes up in the morning and it's in bog 0, 90% of the time it'll stay in bog 0 the next day. But 10% of the time it'll sort of get an idea in its head and sort of jump over to bog 1. And similarly, if it's in bog 1, well, maybe bog 1 is not quite as enjoyably fetid and swampy, so maybe there's only an 80% chance the mosquito will stay at bog 1 and instead will jump. So what Markov shows is in a situation like this, and in fact in a rather general set of such situations, actually the percentage of the time that the mosquito spends in each bog will indeed, just like in Bernoulli, settle down to a very predictable average, which if you guys are, if there's some undergraduate math majors in the room, you can sort of for fun compute what that average is. But of course, it is not true that where the mosquito is on one day is independent from where it is the next day. Quite the contrary. It's very likely to be in the same place one day as it is the next. But this is another example of a random walk, a little bit different in nature from the one that I showed you before, but Markov develops this general theory. And actually, once he has it going, he doesn't stop there. So what he does, well, okay, now I'm jumping forward in time. What I just told you is what Markov was doing sort of simultaneously with everything else I told you. Around 1910 is when Markov writes this paper criticizing Nekrasov. Now we move about 15 years later, if I remember correctly. The one thing, of course, that the Russians can agree on, whether they're atheists or whether they're Orthodox, is Pushkin's poetry. That's important, right? We can all Russians can agree on this. So he then does something rather strange. He's like, well, let me take Eugene Onegin, this great verse poem, and I'm just going to write out the first 10,000 letters of it, and then treat that just like the mosquito jumping from bog to bog. He's going to say, well, let me look at what happens when there's a consonant. What's the next letter? And he found in his sample that there was about a 33% chance that the next letter would also be a consonant, and a 66% chance that it would jump to a vowel. Whereas when the letter was a vowel, there was only a 12% chance that the next letter would be a vowel, and an 87.2% chance that it would jump to being a consonant. Okay. How much do we learn about the poetry of Pushkin from doing this exercise? Like, maybe not so much. But he does, for instance, take another book, I didn't write it down, sorry, but another Russian novel, and finds that these numbers are just different. And somehow even this incredibly meager and reductive analysis is enough to distinguish these two literary works. So this kind of sort of shows you the generality of the theory that can be applied to such a disparate range of settings. This is somehow like letters in the Russian language are not like mosquitoes at all, and yet we can draw this picture, which I hope you'll see, looks very much like the picture I just drew. So we're actually now going to kind of continue with this idea of thinking of linguistic production as something that we can talk about with a Markov chain. Now we are done with this incredible period of 1905 to 1910 when this subject is being developed so many times in so many places. We're going to jump forward to the 1940s and Claude Shannon. I should have put a picture of him too, but I didn't. And actually, in order to do this, and good, we're just at about 30 minutes in, so this is the perfect time. I want to tell you about the Claude Shannon game. But actually, I think, honestly, the best way to explain this is for us to just do it. So, so here's what we're going to do. I showed you on the last slide that Markov thought about language as a sequence of consonants and vowels. Well, that's pretty weak. Like, that's a pretty impoverished view of what language is. We can at least maybe think about each letter as being separate. And Shannon had access to much more computational capacity than Markov had, who had to write everything out by hand with pencil. And so Shannon thought, well, so one thing you could say is, well, what if you had, instead of just consonant and vowel, you had all the letters? Shannon observed that you could even go a little bit farther and think about combinations of letters. And he invented this game that he would play, and I'm going to teach you how to play it, and then we're going to do it. So what I'm going to need from you guys is for everybody to have some source of text. Now, I usually have talked about this stuff in the United States, which is a painfully monolingual society. Here in Singapore, I think I'd better ask a piece of English language text for this to work well in this polyglot society. So if you have like a book on you, that's fine, or if not, you can this is the only time I'll say it's okay to pull out your phone while I'm talking, but if you, and just like sort of find some piece of, we all just need to have access to some sort of decently sized body of text that we can look at. Okay, and while you do that, I'll tell you what we're going to do. Oh, that's a good choice. So we're going to play the game with what are called trigrams, and a trigram is just like a fancy name for a sequence of 3 English letters. So I need one to start with, so just anybody who's looking at their piece of text, just tell me 3 letters that appear in a row. V-A-R? Okay, so I'm going to write V-A-R. Now, Shannon wanted to do something like a Markov process that's going to tell us what the next 3 letters should be. But we're not going to choose 3 letters anew. So here's, I'll sort of draw this little picture. So, that's not what's supposed to happen. Okay. The next trigram, okay, sorry, I'm not sure why it's doing that, but. The next trigram needs to start with AR, so it overlaps very nicely. Okay, so now we're going to start to see what we're going to do. Everybody's looking at your text, see who can do it fastest, and I need you to find 3 letters that start with AR and tell me the next letter. Okay, you've got one. No, she's on first. A-R-V, okay. Okay, so let's see if somebody's reading about Harvard, I guess. I always like that. Okay, so, okay, now somebody needs to find, this could be a challenging one, an RV. Look until you find an R followed by a V and tell me what comes next. What? RVA, okay. You're all reading about Harvard. I love it. Okay. Okay, so now we have a V and an A. Who's got a VA? VAT. VAT, okay. By the way, I should say, one thing that's allowed to happen, I should have said this, if you see, I'm going to ask for an AT, but if that ends a word, you're allowed to say space. I should have said that. That's I mean, anytime you see those two letters, if it happens to come at the end of the word, you can just say space or like whatever it is. So AT, what have I got? Yeah. ATE. Okay. Okay, so now I need a TE.
Space.
TE space. Okay. So now, okay, let's figure out what we're doing. I have an E space, which means somebody needs to find, if you see a word that ends with E, then thus followed by a space, I need the first letter of the next word.
S.
Okay. Okay. And now I've got space S, so I guess I need a word that starts with S, and what's the next letter?
L.
Okay. You guys are getting this pretty fast. Okay, I don't know why that happened. Okay, so I need an SL. That shouldn't be such a hard one. What? Really? SLN? Now you guys are just messing with me. Really? Okay, I'll go with it. We've got to obey the process. Okay, what's an LP? Do you guys see an LP? Okay. Okay. And now a PS. Anybody see a PS? PSY? And how about an SY? Okay. All right. Let's stop there. I think we've got enough. So what did we make here? We made varvate slipsil. I guess that's as best as I can pronounce it. And we could do this for as long as we wanted, and we would be doing something that was rather like what Markov did with Eugene Onegin, but with one important difference. Markov was taking a text that already existed and sort of analyzing what was the probability of going from one letter type to the next. We're doing something different. We're saying we're trying to generate text by somehow estimating, given, let's say, a VA, what's the probability that the next letter is T or something else? And how did I do that? I used you guys as a random sample. I mean, in some sense, you guys have sort of some big body of text, and probably among the texts you guys were looking at, there were lots of VAs, and some of them were followed by T, and some of them were followed by S, and some of them were followed by L, and maybe some of them were followed by Q. I don't know, like in your weird text. And so in some sense, by using you guys as a sort of body of knowledge, and when Shannon did this, by the way, he would just he was by himself, so he would pick out a random book from his library and sort of look through it until he found the bigram. But this is sort of faster and more fun, actually, if we all do it together. But he had this idea that in some sense, by sort of generating a Markov chain on the fly, he could produce something that looked like English text. So this is from his famous paper on the dawn of information theory in 1948. An example of what we just did, a little bit longer. In noist latwe cratix flor bears grossid pondenome of demonsters of the reptigen is regioactiona of cray. This a very, very important sentence in the history of generative linguistic production. And I think what's fascinating about this is that there is something English-like about this, right? It's not English. Almost, let's see, is anything in here? Of is a word. So there's a few things that are actual words, like of and way, but mostly this is not English. And yet I think we can agree that recognizably it somehow comes from English. You would know it was made from English and not French or Spanish or Malay, right? So let me see where I am in my notes. Oh, now I know what I'm ready to do. I'm ready to answer the puzzle. Did you remember there was a puzzle at the beginning? So we had, now you'll remember that at the beginning we had this sort of list of things that looked kind of like words. And let me now tell you where those came from. They came from the output of the exact kind of process I just described for you. Where do they come from? They come from names given to babies in the United States. And the list I gave you, you can see it's number 2 here. It's Kendi, Jean, Abby, Fleury, Mara, Jean, Starlo, Kaming, and Batilia. Those were generated by names of babies born in 1971, the year I was born. So I feel like I have some sense of like what kids born around then have names that sound like. And I want to tell you guys, by the way, I did actually look to see if I could get data of baby names given in Singapore, and I couldn't find it. So I don't know if there's an official government source for this the way there is in the United States. So I did try. What we did in our exercise together was we used sets of 3 letters. But there's nothing special about 3. We could have done that with grams of any length. So I wanted to show you what happens if instead you use bigrams, sets of 2 letters. Well, you can imagine that our system doesn't quite have as much memory. And indeed, the names that it generates are like a little bit weirder and harder to say. Like Tiandola and Baralan, Madrahadria, they're like a little bit more Game of Thronesy somehow. But they probably still are recognizably from English. Whereas, if you use pentagrams, if you use sequences of 5 letters, then actually they're much closer to real names, like so much so that in fact sometimes they are real names, like Adam or Kelsey or Susan, right? If you have S-U-S-A and you're looking in your data of baby names and trying to figure out what the next letter could be, like what the 5th is going to be, well, there's not going to be so many names that contain those 4 exact letters in a row. And so the longer the length of your gram, the more you're going to kind of be like recapitulating what's actually in your data set. So you have this sort of knob that you can turn that takes you from how kind of original you are, but also maybe making things that sound weirder and harder to say, towards how closely you're approximating the data. And just to sort of show you, I did the same thing with baby names of babies born in 2017 and baby names of babies born in 1917. And again, I think you will agree that somehow these 1917 names, they feel more old-fashioned and early 20th century, even though these are just generated by this incredibly mindless process. Okay, so maybe you can see where I'm going with this. We are in a moment where people are super interested in automated linguistic production. I guess it's a little controversial whether we call it linguistic production or not, but let's posit that it's sort of some form of linguistic production. One thing I try to write about a lot because people are very interested in it is just what are some of the mechanisms behind these new systems, these so-called large language models, which I put ChatGPT in the title of the talk, but that's only one of these large language models. I want to emphasize that what they are doing is not so different from what I just showed you. It's more complicated, obviously, but I feel that it's the same kind of thing. And I hope you've already seen that a rather mindless mechanical model can capture some features of English language production. There's one big difference that I think I do want to point out, actually, which is that what would have happened if we started with a pair of letters and you just didn't find it? Like none of you guys could find it. Like if for some reason, if we had a WQ, and I actually looked this up this morning because I wanted to add this to the slides. Of the 676 pairs of letters, there's only 7 that apparently did not appear in any English word, and WQ is one of them. So if we'd somehow ended up at WQ and I'd ask you guys to look, we would just all have been sitting here in an uncomfortable silence while you scrolled through your phones looking for a WQ, and you wouldn't find it. And as you guys probably know, a contemporary large language model does not just look at 4 letters and try to pick the next letter, right? It's looking at like a whole long sequence of words. Okay, so if you have like a 30-word sequence and are trying to predict the next word, well, you're probably not going to find that exact 30-word sequence in some existing piece of English text in the database. So I do want to emphasize that there's something going on here where you're not just sort of looking at sort of some massive Markov chain where every single possible piece of input has a what's the probability of the next thing. For instance, for this, well, actually, what would you put? So here's a question: what would you put if you didn't have? If you looked through all the books in your library and you didn't find any WQ, and yet you're like a good large language model. You're supposed to put a next letter. Correct. I think there's a right answer here, and I think that's the right answer. You'd be like, okay, I didn't find any WQ, but somehow I do kind of know something about Q. And I know that, it does sort of seem like U should probably be next. And maybe this is some kind of neologism, like a cow quake. Like there's a lot of cows like running through the field, like and their feet are stamping so hard that it like shakes the earth, and it's a cow quake. That's like the best thing I could come up with on short. Notice. So so maybe you should think of what the large language models are doing as a little bit more like this. They're not sort of finding this 30-word sequence somewhere in its data set or in multiple places and figuring out how often the next word was cow. Somehow it's saying what things are like this 30-word sequence in some sense that's learned over time. So let me close by the last. I just want to talk a little bit, because it's a subject of great interest, of where I see this stuff going, and then we'll close. So, yeah, if this is indeed a new thing in the world, I mean, as I've tried to argue, it's continuous with things that we've developed before, but people kind of freak out about it, and I want to sort of try to diffuse that a little bit. So this is a paper that I wrote with some folks from DeepMind. And one thing we were trying to do was say, like, well, how well can these large language models? I mean, I think you guys have probably everybody in this room has seen a large language model produce something that looks like English text. We were trying to produce computer programs, and that's probably actually, how many of you guys have used a large language model to generate code? I'll bet a lot, right? Okay, so not the majority of people, but it's pretty good at it. Actually, like much better than it is at producing English text. On the other hand, it's the best at producing code that kind of does a sort of standard off-the-shelf thing, code that's a lot like code it's already looked at. So this was a project, and actually maybe I think I have on the next slide. Yeah, I'll show you some of the code. So what you're looking at here on the left is code that nobody wrote. This is like code produced by a machine. And in a different kind of talk, we would talk more about the mathematical problem that this is trying to solve. But I guess all I want to say about it is that we tried to train a large language model to write a program that would do a good job solving a mathematical problem. Here's what we found. If you trained it very hard on one instance of the problem, it actually did pretty well. Better, to be honest, than I expected that it would. What we were really interested in is whether, okay, what I want to point out is that at the very top of this code, and you really don't have to know very much about code to know this, there's a variable n, and in the program on the right, you see a little thing that starts with n equals 8. So what I'm just going to say, without talking too much about technical math, because this is not that kind of talk, we were trying to solve some 8-dimensional problem. That's why it says n equals 8 at the top of that code. And we trained it on a lot of examples in 8 dimensions, and we actually got like pretty good performance and like found a new example that was like better than any previously seen. Unfortunately, if you run that same program with n equals 9 or n equals 10, it doesn't work. So this is a problem called generalization. I think this is a kind of frontier that in some sense we have not mostly yet solved with these large language models, sort of extrapolating beyond what they're trained on. So maybe to sort of say a little bit about just what I learned from working on this project, a few things. First of all, I want to emphasize that even though we're very obsessed with large language models, machine learning and AI are like a very big field that like have like a lot of other techniques that sort of work really well for certain things. I'm not sort of so convinced that large language models are the general tool that does every single problem. There's sort of specific tools for specific problems that are still very much alive. This is kind of how I see it as a mathematician who works on these kind of problems. So okay, last picture. Like who's this? Do we know who this is? I thought this one was going to be easier. Alan knows who this is. Really? Okay, this is David Byrne, the singer from Talking Heads. This is a still from the Burning Down the House video, and I bring it up because I think of David Byrne as kind of a model for what the relationship between AI tools and creativity can be. Because the way, the way the lyrics to this famous song were written was basically the band playing and David Byrne kind of barking and making noises into the microphone in a way that sort of fell right with the sounds. And then the band kind of going back and be like, well, what does it sound like he's saying? And this is how the words were written. And I think in some sense, the sort of appropriate way, at the moment at least, to think about the relationship between large language models and the creative industries, of which I like to think of mathematics as one, is something like that. These models are like a Markov chain, producing something that in some sense is random and mechanistic. But on the other hand, if you look at those baby names we made up through this very simple process, like some of them are pretty good. I like Madrahadria, that's one of my favorites. Like you can imagine a process like that actually kind of maybe not naming your baby for you, but kind of giving you some ideas about how to name your baby. Maybe you would do something with that input that would actually sort of jog you out of like naming your baby Jaden, like everybody in America always does. Like you could think, that. So I think we can be a little bit like this. So I have a slide, right. So the goal of these things is sort of not to replace human ingenuity and human creativity. Well, but there are probably some people who think that's the goal. I don't think that's the goal, and I don't think it's that likely. But I think there is like a huge amount of potential for actually augmenting what we as humans do. These machines are very eccentric in the output they produce, and that can help us think of things in new ways. They just sort of explore and sort of show us things that we might not otherwise have seen, but they're things for us to do something with. And so maybe I'll just close with this. I think at least in terms of two things I know pretty well, like writing and doing mathematics, I think there's a feeling that as these machines get better and better, the idea is that they're going to excel humans in all domains. And I think in some domains, look, the fact that a machine can excel humans in some cognitive domains is not very controversial, right? Machines are certainly like much better at like multiplying large numbers together than we are. The list of those kinds of tasks will certainly get longer. But I think by and large, it's actually more important. This passage I'm showing you on the picture. This is my like one picture diagram of like what AI is doing. The things we're excellent at will probably sort of stay excellent at, but most of us are not excellent at most things. So actually the ability, I like to say the sort of AI is like right now, it's like mediocrity at scale. And that's not an insult. That's actually something super awesome. Because not only are most of us not excellent at most things, most of us are not even mediocre at most things. And the idea of sort of bringing us from sort of sub-mediocre to mediocre performance. Well, okay, for me, I'm just to be honest, we talked about producing code. For me, it's coding. That's like an area where I, not incompetent, by the way, because if you're incompetent, you won't have any way of judging whether what you're producing actually works. But I definitely would call myself a sub-mediocre coder. I think for all of us in that position, going from sub-mediocre to mediocre at scale has a huge amount of value. So that's my last slide, guys. I'm going to stop there on this journey. I hope I've made all this seem like a little bit less mystical to you, and I hope you'll stay away from mosquitoes. So thank you guys so much for coming. And and I'm happy to take questions.